God morgen. Jeg håper at alle dere hadde god påske, og velkommen til vår webinarserie God forskermorgen. Dette webinarserie er organisert i samarbeid av Multiconsult og Hydrosen, og en gang i måned kommer en forsker fra Hydrosen og presenterer sin arbeid til oss i bransjen. This presentation will be in English, so I'll continue in English. My name is Filip Patočka. I work in the hydropower section of Multiconsult, and I have a pleasure to present Theo Desert, who is a postdoctoral researcher connected to Hydrosen. It was wrong in the invitation, sorry Theo. You are not PhD candidate, you are a postdoc for the last 4 years. Theo will share his research into stability of rockfill dams and riprap protection exposed to overtopping with us. If you will have any questions, you can write them into the chat or simply keep them to the end of the presentation. We will have 15 minutes to address these. And as I said, the webinar is recorded. You can go on, Theo. Your microphone is muted now. So please mute.
That's good. Thank you very much, Philip. Thank you for the invitation, and thank you for connecting today to hear my presentation. So I hope you can already see my screen.
Yeah. Yes, we can.
Yeah, perfect. So as Philip said, I'm a postdoctor that's just started in October 2021 at NTNU. So my topic is focused on stability of rockfill dams and riprap protection exposed to overtopping, and my work is supervised mainly by Fjóla Riksdóttir and mainly funded by NBE. So I don't know how much you are familiar with rockfill dams. At least I can recognize some names. So I know that some of you, at least many of you, are really familiar with them, but I will assume that you are not, all of you. So let's start about a bit of introduction about that topic. So in Norway, we have over 180 rockfill dams that are considered as big dams, so over 15 meters high. And there's a constant increase of the demand on dam safety standards, so that many dams are expected to be upgraded in the near future. From the ICOL statistics, we know that overtopping is the primary factor of dam failure. So that overtopping mechanism needs to be really looked at. So we have extreme flood events arising from the effect of climate change. So there is a need to equip the dam with defense mechanisms in order to safeguard the dam structure. So if we go a bit more into the detail of the overtopping mechanism, when we have overtopping condition, we have the downstream slope of the rockfill dam that is subjected to highly destabilizing forces. And those are generated due to both turbulent through flow, which is basically the overtopping of the dam core, but also overflow, which is the overtopping of the dam crest. So the through flow mechanism just provide internal erosion destabilization of the embankment inside the dam with an increase of the pore pressure, while from the overflow, we get external erosion processes. So we have two key components in order to safeguard the dam, which are the ripraps and also the rockfill dam toes. So from the toe, located there on the pictures, this toe can provide efficient expulsion of the seepage from within the dam, which decreased internal erosion and can then reduce the pore pressure. While the riprap, and we will focus on that aspect today, can protect against the external erosion due either to overtopping, as we said, or to accidental leakages. So my topic, and the objective of the postdoc basically is to investigate failure mechanisms in riprap and rockfill dam models that are subjected to through flow and to overtopping events, and such result would be valuable to predict and assess the risk of rupture, as well as to improve the construction and reinforcement techniques of the dam. So I have split in my presentation in different topic, different subsection, let's say, which correspond to different work I've been submitting or presenting in different conferences or journal articles. So first I will start with an article that was published as a special issue in the Water Journal, which is an article about riprap protection exposed to overtopping phenomenon, and it's basically a kind of review of the laboratory experimental model that we've had in the hydraulic lab. So it's not only my work, but models that were already built before I started. So the common characteristic of all the experimental setup are those ones. So basically, were all built in the hydraulic lab at NTNU, and they were built in that red flume that you can see there. So it's quite big flume, 25 times 2 times 1 cubic meter. And we built model that are considered to be 1 to 10 scale model of rockfill dam. With particularity is that we have a very steep downstream slope of 1/1.5. And for all the models we've been building, we've been choosing the material dimensions according to the NVE guidelines, so the Norwegian Water Energy Directorate. So basically what we do is we build the model and then we expose them to incremental overtopping discharges. So the discharges levels are maintained constant over a regular time interval in order to have the flow stabilization at each overtopping interval. And then basically what we do is repeat the procedure until we have the complete failure of the model. And this is what we're looking at. So I hope you can see the animations. So the first model to be built, they were built by Priska Hiller. We did a PhD first, and then it was also done again during Ganesh Ravindra's PhD as well, that came afterwards. So first, to study the stability of riprap, they were built on a ramp without any shell material below, just a layer of filter material with homogeneous grain size. So you can see we have two different configurations of riprap, basically. On the left side, you can see is what we call dumped riprap. So dumped riprap stones are basically randomly placed stones. We just put them on the downstream slope without really paying attention to the position of the stones. Whereas on the right side, you can see placed riprap stones. So those placed riprap stones are stones that have been placed manually in an interlocking pattern so that they really fit together well. So it takes a bit more time to build those models. And the thing is, they are much more resistant to overtopping. So when we expose those two models to overtopping discharges, in yellow there, what you can see is what we call the critical discharges. So basically, for which discharge level does the model fail? So for dumped riprap model, the model failed at 40 liters per second, while for 275 liters per second for the placed riprap model. So you can see the difference of resistance between both models. But the point of those models, very important, and I will discuss about that later, is that both models were supported at the toe. So unfortunately, you cannot see it on the picture, but there is a toe support just over there, just behind the column, just maintaining the whole structure together. And at the toe structure, at the toe support, there is also some load cells in order to measure the load. So from those experiments, we could measure the stone position from laser measurement from individual stone, and I will come back to this later, and also the loads, as I said. So another important aspect of an important difference between those two models is the failure mechanism. What we observe is basically an external erosion process of the damp riprap layer as a failure mechanism, while we observe a sliding and even a buckling process for the damp riprap layer that is supported at the toe. So when I say buckling, it's basically a deformation in the X, but also Z direction of the whole riprap layer. So that was the topic of Ganesh article. So then what was done in the flume is build the same models, but basically unsupported at the toe. So I have some video now. So basically what you can see for the dumped riprap model, we have some external erosions starting at the crest and then, eroding the whole layer basically. And what is interesting to see is that the models break at the same level as when it was supported at the toe. So basically, the toe support doesn't bring an improvement in the resistance of the dumped riprap layer. However, for the placed riprap layer, you can see that the resistance is much higher when we have toe support. Just come back to the previous slide, 275 liters per second when it's supported, only 60 liters per second when it's not supported. So the toe support definitely has a huge impact on resistance. And still we observe the same failure mechanism, the whole sliding of the layer instead of external erosion. Everything just slides at once we reach the critical discharge. So from this model, Ganesh in his PhD could invest the movement of the stones from PIV technique and also the use of smart stone probes. Then what was done is basically build model with shell material below. So also during Ganesh PhD. And so we could just try to understand the impact of through flow. So as you can see, the critical discharges are like twice less important as when we did not have the shell material. So for the model with damp riprap, we have some external erosion, reducing the steepness of the slope, and then continuing eroding the shell material after eroding the riprap and the filter material. For the placed riprap layer, we observe same mechanism as we had on the ramp, full sliding of the whole layer once we reach the critical discharge. So both of this model were not supported at the toe. So during my postdoc, I could build the same kind of model, but this time supported at the toe. And the point of such work was to see if we were still seeing and understanding the failure mechanism I told you earlier, which is the buckling. So basically, we have the sliding of the whole placed riprap layer, but before the sliding, we have a deformation of this riprap layer, which we call the buckling, with a deformation in the X and Z direction. So the improvement also during those tests is that we could measure the displacement of riprap, but not only from laser measurement as it was done before, but also using structure for motion to see the whole deformation from a 3D models. And we could also measure the load at the toe. And then finally, during Georg Kiplerson PhD, he could build models with not only the downstream part of the dam, but the full dam. So for both placed and damp riprap model, and we observed the same failure mechanism. So with damp riprap model, guess what? Surface erosion, external erosion, yeah, reducing the steepness of the slope, getting slowly eroding the material. And what we will be observing for the placed riprap layer is something just as before from half that model, something much more sudden with a whole sliding of the riprap layer. So there it is for placed riprap. So it's a totally different process. Yeah, everything just slides at once. So that's mainly the difference between both models. With placed riprap, more security, it resists more time. You see the critical discharge is higher, but when it fails, it really fails more suddenly. So Georg could also work on structure for motion and using pore pressure cells to investigate that topic. So I can draw some research conclusion from those historical work that were done. So first, the role of toe support. So what we know is that there is no impact on the surface erosion mechanism of individual riprap stones for dumped riprap models, and there's no benefit to dumped riprap models where the protective layer does not act as bearing structures as it does with placed riprap. So for the placed riprap model, the sliding phenomenon has been described for unsupported riprap, and we have what we call buckling process for the supported ones. And the supported placed riprap are much more resistant than the unsupported placed riprap. Then there's, as I said, big difference between damped and placed riprap. So when we have placed riprap, when the protective layer consists of interlocked stones, the failure mechanism is always a sliding process. So with buckling when it's supported, and it's always a surface erosion process for damped riprap models. We observe supported riprap models to be 7 times more resistant than supported damped riprap ones, and all the other unsupported placed riprap models demonstrated a resistance still 1.5 to almost 2.5 times superior to damped riprap ones. And finally, the impact of through flow. Definitely the through flow has an impact on the resistance of the model, making them less resistant. So it has an impact in the whole stability of the dam, as we could guess. So it's very important to keep on studying the riprap layer deformation and evolution with shell material below when we're working on overtopping phenomena. So then I had the opportunity to present my work in IAHR conference in Spain last year, and also publish an article in Water Journal on placed riprap deformation. So it's about the model I just introduced to you. This is the model that Ganesh built during his PhD. So he collected some data that it did not have time to process and to publish. So I kept on with the work. So basically we had, as you can see, the placed riprap layer of a filter layer without shell material. And we could measure the load at the top from 6 load cells, but also the position of individual riprap stones that you can see in blue. So basically 6 riprap stones, 1 on the crest and 5 on the downstream slope. So we could expose the model to overtopping discharge level that were maintained constant over a regular time interval. So that time interval was 30 minutes in order to have flow stabilization at each overtopping interval, and with incremental overtopping of 25 liters per second. So as for the other model, we repeat the procedure until the total failure of the models, and Ganesh had the opportunity to carry out 5 of those tests. So what you can see now on this graph is basically the load values on the y-axis and the length from the toe on the x-axis. So basically, this is the load that we measured when we are building the riprap layer. So when we are placing the stones manually. So you can see that the load increase when we are building the layer. We're building it from the toe to the top. And when we reach around 50 centimeters, then there's no more increase of the load. So there's a stabilization in the load, and then just the interlocking forces compensate the weight of the load. So then here what you can see is basically the load values, but measured during the overtopping processes. So you have different colors, different symbols. Basically, the different symbols stand for the 5 different tests. And the different color stand for the different contribution of the load. So in black, what you can see is the total load measured at the toe. In yellow is the contribution from the riprap stones, and in blue, the contribution from the water overflowing the model. So what you can see is that the contribution from the riprap is more important than the contribution from the water, and that it increases along with time, along with the increase of water. So basically, the water just compact more the riprap layer, increasing the load measured at the top. So we could draw like easily some linear relation between the load and the discharge level from those models. And then what was investigated was stone displacement. So Ganesh did that previously in his paper, basically relating the discharge level with the displacement and with the buckling of the stones. But from those data from the load cells, we could also get the same kind of relation, because there's a strong relation, as you can see, between discharge and load. So we could draw the same relation between loads and placed riprap displacement when they are supported at the toe to express the buckling. So basically, in the y-axis is the displacement in the z direction, just taking into consideration that we rotated the coordinate system so that it fit in the direction of the slope. So going in the z direction, and also the displacement along the slope. So you can see that the deformation gets more and more important as the load increases, so as the discharge increases. So there's progressive displacement in both x and z direction. And we can see also that the magnitude of elevation in that direction, so the magnitude of the buckling, basically, really depends on the position of the riprap stone. So the more you are kind of in the center of the model, the more it really buckles. And the whole compaction of that placed riprap layer then generates a gap at the upstream part of the model, close to the crest. And then that's that buckling mechanism and the generation of that gap that basically generates the complete breakage of the structure once we reach the critical discharge value. So that was one of the work I could do. Then now I'm going to present the 3D displacement, which is quite related to what I just showed you, but we use a more advanced technique without just relying on individual stone position measured by the laser. We use structure for motion in this work. So let me introduce that to you. So as you can see, basically we have the same models as the one I just introduced to you. Big difference is that we have shell material below. So that model allows the through flow mechanism to occur. So the model is supported at the toe. We have some load cells. And basically for that test, we built 4 different models. So I didn't build all the models myself. I was helped, fortunately, by some master students, because it gets really heavy and time consuming to build those kind of models. I can't remember how many kilos or tons of material we have, but surely Georg person that is present there may be able to answer that question. But we have to use shovel, barrow, and use strength to build those models. So it takes a few days to do. And the big difference between the 2 first models we built and the 2 last models we built is the compaction of the placed riprap layer. So basically, test 1 and 2 were having their riprap layer compacted during the construction. So basically, we're placing the riprap stones individually, and then we were stepping on them to make it real compact. For test 3 and 4, however, they did not have the riprap layer compacted. So we were using a ladder parallel to the slope, and then walking on the ladder and really placing carefully the stone to make sure we don't put too much pressure on them while we build them. So it's an important point for that study. So as I said in previous slide, we observed a sliding phenomenon. So the point of such work was to see if we could really observe the buckling phenomenon that was described for placed riprap supported at the top but built only on a ramp. Spoiler, yes, we did. But what is important on that slide is to see the big difference of resistance to overtopping. So this is the critical discharge value. So big difference if we compact or not the riprap layer. So remember, test 1 and 2, placed riprap layer, compacted. See the resistance to overtopping, like in average 200 liters per second. Now look at test 3 and 4, placed riprap layer, supported at the toe, same thing, but not compacted. Resistance only 100 liters per second. So there's clearly an impact on the compaction. However, what is quite interesting to notice is that even though the critical discharge value is very different from compacted to uncompacted test, the critical load measured at the toe is not that different. So we're still in the same range. So that was quite interesting to observe. So as in the previous study, we could plot the load measured at the toe during overtopping according to the overtopping value. So in gray, what you can see is the data from previous study. So when riprap were only built on a ramp, and in blue and orange are the data from the test with shell material with through flow. So what you can see basically is that the load are much more important when we have shell material below, and this is can directly be impacted to the through flow. And also we can see that from the orange data that test 3 and 4, the loads tend to increase faster than for test 1 and 2. So remember, test 3 and 4, non-compacted tests. So from the first overtopping, we get a compaction of the riprap layer that was not compacted during the construction, and this make the load increase faster. So then the thing is, we could stop the overtopping discharge. So we started, I think, at 50 liters per second. For 30 minutes, we overtop the model. Then what we do is we stop the flow. We basically take as many pictures as possible all around the model. And then we restart the flow, increasing it by 25 liters per second. So bringing it to 75 liters per second. We make the flow run for 30 more minutes, then we stop the flow, we turn off the pump, and we take many, many pictures of the model. And from those many pictures of the model, for each different discharge value, we're able to make 3D models using structure for motion technique, so using Agisoft Metaship software. And those models were really useful to increase our knowledge and our understanding of the deformation of the riprap layer. Because before we were using just laser measurements, so basically using only 5-6 position of riprap. Now we can basically use the position of there is more than 1,000 riprap, so it's much more representative. So to understand how to read those pictures, so at the top of the slide you can see digital elevation model from test 1 and 2, and at the bottom from test 3 and 4. So test 1 and 2, remember, compacted place riprap, test 3 and 4 non-compacted. So on the left side, that's basically the upstream part. The flow is running from left to right, and so on the right part is the toe of the dam. And those digital elevation model, they were obtained directly from the 3D models. So we are considering the 3D model at the initial position of the riprap, and then the 3D model just before the failure occurs. So we can just see the movement of the riprap from their initial position to the last moment before the breakage. So it's quite interesting to see that the movement first in the X direction, so downstream, is much more important for test 3 and 4 that were not compacted. You see the orange arrows, they are much larger for test 3 and 4 than they are for test 1 and 2. Also, what you can see is the difference in elevation. So the more the color tends to white, the more there is an increase of the deformation in the Z direction. So what you can see is clearly the buckling that was described before, but now you can see it from the whole layer for a full model that was, I mean, half model that was built with shell material below. So the difference between compacted test and non-compacted test is quite striking because you have the generation of the gap that you can see here just after the crest. You see the crest doesn't really move, the stones just stay the same, and then we have the generation of that gap and the sliding of the place riprap layer generating the buckle that was described by Ganesh before. And that movement is less important for compacted test, and because that movement was less important for compacted test, the gap was less deep. Then the structure was more stable and was more inclined to resist to higher discharge values. So from those data, we were able to plot some graphs because you know that we like graphs in science. So we could just plot the deformation along the Z direction and also along the X direction. So basically what you can see along the Z direction is like for the 4 tests, we don't have really much movement on the crest. And then wrap, the gap is generated. And then this is basically the buckling and not much deformation at the toe because it's supported by the metallic toe support. X displacement, the same. Stone don't really move at the crest, and then when we just, there's a slope rupture of almost all the stones just slide at once, and then they keep on sliding, but less importantly, till the toe position. So the research work conclusions we could draw from that is first the impact of through flow on the load values that were measured, because we can see a difference between test with and without shell material. Also the buckling that was described for models built only on the ramp without shell material, it was observed, and also it was, let's say, observed in a more representative way with a structure from motion technique. Also, even though we have difference of resistance in the compaction, we still observe the same trends, both in X and Z direction of the place riprap for whole a different test. And also what needs to be pointed out is the grid variability in critical discharge values according to construction methods. So we cannot just rely on the critical discharge value to estimate when a dam will break or not. It really depends on the design of the model, and this is very, very important to be pointing out. It might be even more true for a real dam than for those models that we are quite controlling, right? Because they are still small. So then don't worry, I won't go into the details of those equations, but this is just a snapshot of what I'm doing right now, because I finished a bit studying those riprap stability in my first year of postdoc. Now I'm more focusing on parametric bridging equations. So in the literature, we have many bridging equations trying to estimate bridge width, peak outflow, bridge formation time. But it's very hard to know which equation really fit best for which kind of model. So this is basically my work right now. So I'm using basically mainly Gehrke-Keplersen models. So full dam models, both protected, unprotected, protected with dam, with place riprap, without core, and try to see which equation fits best to which kind of design. So I will not present the results right now because I'm just finishing the article to be submitted with Gehrke. But yeah, just a small spoiler. Xuanzang and Freilich from 2016 seem to provide from now the best results. Then also focusing on exactly the same topic, on the suitability of those equations, but try to see the validity from not only the experimental model we built in the hydraulic lab, but also from the impact project you may have heard of that was held in Norway. Was it, yeah, 20 years ago from now on, so it's been quite a long time, but still we have the data, so we can work with them. So it was on Korgens dam. So I'm taking the data from 3 different models. So one from an earthen dam, so homogeneous clay-fill dam, one from homogeneous gravel dam, and one from more complicated dam with non-cohesive rockfill material with a core, or central mooring core. And so I'm working on the development of the bridge when they are exposed to overtopping. So we can get some better pictures to understand the opening of the bridge. So we can talk more about that if you wish, but I don't have any more results to show from now on. I think it's the end of the time, so I'm open to any question you may have. Thank you.
Perfect. Thank you very much, Theo. That was a very interesting and very informative presentation. I know that we have some people in the meeting who were either cooperating with you or were around when you were doing your study, so I hope they can come with some comments or questions. You can either raise your hand and I will unmute your microphone, or write into the chat. We have 2 questions, quite related, from Mats Bilstein. He's asking about what are the takeaways for dam owners, and what are your recommendations to dam owners with embankment dams in order to increase the dam safety?
Yeah, that's a very open question, because that's basically the whole problematic of our work. I would feel sorry not to not have like a clear answer to your question. I wish I could. So, but I can try to go deeper as I went in my presentation. First, I must insist on the fact that we are mostly only using experimental model in the lab. So there is also all the time big limitation, and we know we should take the results we get with lots. We need to consider them carefully, because the results we get are first limited to the design of the dam we have. So we're using very steep slope for specific property of materials, very specific density of stones, very specific size of stones, even though we are following NVA recommendation, but still. What we can suggest is that definitely, as I said, the toe support has an impact on protected embankment dams for placed riprap. Indeed, like really those models, when we support them at the toe, they can really hold a much more important critical discharge value. So this is the point we could highlight, and it seems apparently useless to do so for damped riprap models. Also from different studies, we can also see that the toe to ensure the expulsion of the flow of the internal pressure, this also helps a lot. So those are key parameters. And then what I could recommend from the last study we made also is to focus on the displacement of riprap. So especially after some overtopping processes, it may be more suitable to look at the displacement of riprap layer to estimate when the dam is in danger than just to focus on the critical discharge flow values. Because as you can see, building the same models, but just compacted them differently, and you have a total different resistance to overtopping. So this is also an important point, I would say. And finally, the use of the equations. I don't know how much you use the equation to estimate the resistance of your dam, but from what we're seeing, the parametric bridging equation, some of them really provide results that are far from what we get from our experimental model. So they also need to be used carefully, because you have some equations that are supposed to fit to embankment dams in general, but when you look deeply in the literature, they mostly focus on an earth-fill dam and not that much on a rock-fill dam, though that's also something that should be taken with great care, I think. I hope that answers your question. This is a whole wide topic. We could talk about that for ages, but yeah, thank you for the question.
Thank you. There's a thumbs up from Mats. I can ask while we are waiting for more questions. We have seen on the videos from the failure on the dams which had the riprap layer compacted that the failure comes quite suddenly.
Yeah.
Did you observe any, or did you identify any warning signs that you got a feeling now it's coming close to the critical flow?
I guess that's the thing. You can guess from previous experiments, you know more or less which critical discharge value this should break. But when we just lead our test, we're just sitting on the side of the flume. So we have a glass side of the flume, so we can directly watch the model. And unfortunately, no, it's not easy to say now it will break. It's just come whole of a sudden. So it's quite exciting. But then when we investigate that data, then we can understand, for example, the displacement of the riprap layer. So if we were able to have those 3D models directly live, then we could see the movement and we could clearly see the generation of a gap. And then you can guess when you have that gap on the crest, you can say, yeah, it's more likely to break because we have a gap that is more important. But you cannot say right now, I think within 1 minute it will break, because sometimes we know that the previous model that was built exactly the same way broke at that discharge level. So then you are looking for the next model to break at more or less the same level of discharge, but sometimes it takes more time and you're waiting for 30 minutes more, 1 hour more, and still it doesn't come. So you just know you have 1 or 2 hours where you should be staying and not go to the toilet to make sure you see the breakage, but you cannot be exactly sure when it will be coming. No.
That was pretty much a guessing game.
Yeah.
We're trying to guess and failing often. Oh, it's going to come now. Nah, and then we're waiting another hour.
Yeah, and that is what I suppose is very scary for the dam owners, that it is so unpredictable.
Yeah, but still, as you can see, for example, for those models that I have, the protected model with place riprap supported at the toe, as you can see, critical discharge value is very different if the model are compacted or not. But still, the load value are not that different, though that could be a tool, indeed, to really measure the load at the toe. And then when you reach that critical load values, it's quite more reliable indeed than the critical discharge values. So this is an important parameter to look at.
One thing I could comment that you didn't mention, I think, was on the different thicknesses of dumped riprap.
Yeah, I didn't go into that.
There we saw some interesting things as well. That some tests were done with a thicker dumped riprap layer than Ganesh's earlier tests, and those failed quite differently in that you had an initial displacement, but not sufficient to initiate a full failure. So there was a sliding, but then it stopped, and then we had to ramp up to a much higher discharge until we could actually get a failure.
Yeah.
But that drawing any general conclusions from it is a bit tricky, because yeah, that would be maybe for lower dams with a fairly thick riprap, but that wouldn't be relevant for a very high dam, for instance.
Yeah, thank you very much. Ravindra has hands up, and you can unmute your microphone.
Can you hear me?
Yes.
Yes. Hi, Theo. Thanks for the very nice presentation. Just maybe to supplement what you've been talking about and to go a bit on the question we got from the person from Vattenfall. I think it's basically important also to think about uncertainty with the whole design aspect, because when I'm a dam engineer, I'm designing a structure, I want to be as minimum uncertainty with the end product as possible. As far as I can understand, and I've been working on this as well, and Theo and Helge has been working on this as well, I hope everyone agrees that when we compare dumped and placed ripraps, there is much more uncertainty associated with the design of a placed riprap because it's so complex. There are a lot of parameters affecting the end product or the stability. Basically, you can think about the toe support, as Theo been mentioning, the placement method, the quality of placement, and the stones interconnectivity between the stones, angular. There are so many parameters affecting the stability. But when it comes to dump ripraps, I would say the uncertainty margin is much smaller, so you can be more sure of the end product. Also, when you think of the design perspective, there's much more literature available internationally on dump riprap because they've been used over many decades. And also the equation we're using in Norway for the design of placed ripraps, yeah, we have looked into that, and we can see that they're not really applicable, or they've not been developed for placed ripraps. They've more been developed for dump riprap. So I think in general, it's important to understand where you get, most for, most for your basically efforts for constructing the riprap, and also thinking about the toe structure. As you say, it is a parameter which affects everything, but again, it's a very complex thing how to design the toe structures. So I don't know if you can maybe talk about on that, but general, I think we just need a better holistic perspective when we think about design of ripraps for embankment dams, and in general erosion, basically protecting against erosions.
Thank you, Ganesh, for pointing that out. That's very important matter and very deep thing as well as be able to quantify the uncertainty, because I didn't go into the detail in that presentation, but yeah, from the models you've been building also during your PhD, you can see like placing the riprap, and basically we are controlling the thing because we are in the lab, so we are just over the whole layer placing them manually, and still we observe like very different critical discharge value for what are supposed to be the exact same models. So just you can imagine that for real dam it would be much more tough to estimate the critical discharge value. And yeah, about the toe support that you mentioned, there is no clear guideline for building those toe support and the NVA guidelines, so it's very complicated to know also our representative our toe support is to real toe support that we could find on the field. And Ganesh also published an article on that. They went on the field. Maybe you want to talk about that, Ganesh, about trying to investigate the different toe support that you could see on the field on rockfill dam, and very different kind of toe supports, some without any real explanation of their purpose, but
but also another important thing to remember is basically that we have been saying that placed ripraps are stronger than dumped ripraps. But again, I'm thinking the objective is to design a riprap for a given overtopping discharge and not to build a stronger structure. The question is, okay, stronger, what does it mean stronger compared to what, to why? I think for a given overtopping discharge, you will get very much minimum uncertainty when you choose a dumped riprap compared to placed riprap, because the uncertain margin is so huge. There's so many parameters. And also, I think we should come up with a method, and we're working on this. We're coming up with method where we need to look at different situations, for example, through flow and overtopping, and come up with strategies to secure the dam against damages. So I think that's also a very important thing we're working on here, and that would be really interesting to collaborate on that further. It's basically that we need to understand there are different failure mechanisms, and every dam is different. Right now, there are these constants in the regulation saying that, okay, every class 4 dam should be dimensioned for 0.5 or something like that, 0.7. So I think that's also a tricky thing to give fixed numbers. I think we should take every dam as a case and then look at the strategy for how to stabilize the dams. Yeah, sorry for the long comments.
Thank you.
I comment a bit as well. And I agree with what you say, Ganesh, about the dumped versus placed as well. That yes, placed riprap has a potential for withstanding a huge amount of overtopping flow, but there are serious buts there in that it requires a good tow. Otherwise, it's not pointless, but it's very much lessened in effect compared to an unprotected tow. And placement, how it's constructed, is very important. And also, you talk about we need to design for an overtopping discharge, because I've been looking a bit roughly on it, seeing that, okay, for some of the big rockfill dams we have, they cannot feasibly, with any kind of PMF or few times the PMF, get an overtopping that's sufficient to generate a failure, because the whole dam is a kilometer or more long spillway. Whereas for other dams, you can easily get high enough discharges to fail it. So that's also something to consider, whether we need to differentiate between where can you feasibly get enough water over the dam to actually have a problem.
I agree. Yeah.
Perfect. Thank you very much. We are a few minutes over, so I think we should end here. Thank you very much, Theo, and thank you for your contribution, Geir Helge and Ganesh. We can as well say, in the end, as Mats was stating here, there is ICOLT annual meeting in Sweden from 11th to 15th of June. So for those of you who are interested, please go to the website of ICOLT and register for it. And with that, thank you very much for today's webinar.
Tusen tack.
And have a good weekend.